you can see Einstein's theory of relativity under light. One of that is an implication. Relativity is one of the most famous scientific theories of the 20th century. But how well does it explain the things we see in our daily lives? Formulated by Albert Einstein in 1905, the theory of relativity. It is the notion that the laws of physics are the same everywhere. The theory explained the behavior of objects in space and time. It can be used to predict everything from the existence of black holes to light bending due to gravity to the behavior of the planet Mercury in its orbit. The theory is deceptively simple. First, there is no absolute frame of reference. Every time you measure an object's velocity or its momentum or how it's experienced time, it's always in relation to something else. Second, the speed of light in the same no matter who measures it or how fast the person measuring it going. Third, nothing can go faster than light. The implication of Einstein's most famous theory are found if the speed of light is always there.
Electromagnets. Magnetism is a relativistic effect, and if you use electricity, you can thank relativity for the fact that generators work at all. If you take a look of wire and move it through a magnetic field, you generate an electric current. The charged particles in the wire are affected by the changing magnetic field, which forces some of them to move and creates the current. But now, picture the wire at rest and imagine that the magnet is moving. In this case, the charged particles in the wire, the electrons and protons, aren't moving anymore. So, the magnetic field shouldn't be affecting them, but it does, and a current still flows. This shows that there is no privileged frame of reference.
Global Positioning System. In order for your car's GPS navigation to function as accurately as it does, satellites have to take relativistic effects into account. This is because even though satellites aren't moving at anything close to the speed of light, they are still going pretty fast. The satellites are also sending signals to the ground stations on Earth. These stations in the GPS unit in your car are all experiencing higher accelerations due to gravity than the satellites in orbit. To get that pinpoint accuracy, the satellites use clocks that are accurate to a few billionths of a second, nanoseconds. Since each satellite is 12,600 miles, 20,300 kilometers above Earth and moves at 6,000 miles per hour, 10,000 kilometers per hour, there's a relativistic time dilation that talks on about 4 microseconds each day. Add in the effects of gravity and the figure goes up to about 7 microseconds, that's 7,000 nanoseconds.
Gold's yellow color. Most metal are shiny because the electrons in the atom jump from different energy levels, or orbital. Some photons that hit the metal get absorbed and re-emitted, though at a longer wavelength. Most visible light, though, just get reflected. Gold is a heavy atom, so the inner electrons are moving fast enough that the relativistic mass increase is significant as well as the length contraction. As a result, the electrons are spinning around the nucleus in shorter paths with more momentum. Electrons in the inner orbital carry energy that is closer to the energy of outer electrons, and the wavelength that get absorbed and reflected are longer. Longer wavelength of light means that some of the visible light that would usually just be reflected gets absorbed, and that light is in the blue end of the spectrum. White light is a mix of all the colors of the rainbow. But in gold's case, when light gets absorbed and re-emitted, the wavelengths are usually longer. That means the mix of light waves we see tends to have less blue and violet in it. This makes gold appear yellowish in color since yellow, orange, and red light is a longer wavelength than blue.
Mercury is a liquid. Similar to gold, mercury is also a heavy atom, with electrons held close to the nucleus because of their speed and consequent mass increase. With mercury, the bonds between its atoms are weak, so mercury melts at lower temperatures and is typically a liquid when we see it.
Old TV. Just a few years ago, most televisions and monitors had cathode ray tube screens. A cathode ray tube works by firing electrons at a phosphor surface with a big magnet. Each electron makes a lighted pixel when it hits the back of the screen. The electrons fired out to make a picture move up to 30% of the speed of light. Relativistic effects are noticeable, and when manufacturers shaped the magnet, they had to take those effects into account.